Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on filter design. On the part 18 series, I actually discussed how can we actually design a bandpass filter with short circuit stub. For this video, I'm going to emphasize using another method. So instead of short circuit stub, I actually want to use open circuit stub to implement a bandpass filter. So this will be the objective. This video, I'm going to show you a quick comparison between the open circuit and also the short circuit. What are the advantages and the disadvantages based on these two methods? And basically with this, you have a choice whether you want to design a short circuit stub or an open circuit stub. But in general, whatever that I discussed on part 18 will be still relevant for this video. In fact, you can see that basically from the short circuit stub, I actually just need to do a little bit of increment, and therefore I will be able to fulfill a bandpass filter using an open circuit stub. This will be the part 19 series discussion on filter design. The rest of the video on filter design, I have put the playlist under the description. So please take a look on those videos if you seriously want to know more about filter design. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and also the subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, sincere thanks for your strong support. Let's do a very quick recall based on what we have discussed on the part 18 series of the filter design. In the part 18 series, I actually discussed how can we have a synthesis method to design a bandpass filter using the short circuit stub and also the connecting line. In that particular video, I have shown step by step how can we actually obtain all the admittance value on the connecting line and also the short circuit stub. Basically, this is actually the outcome of the part 18 series discussion. Based on all the admittance value, I actually can design a bandpass filter. However, I want to highlight a big major issue about short circuit stub. When I actually implement a short circuit stub, which is denoted as a schematic as a grounding point, what I actually need to do is basically at the PCB layer or microstrip line, I actually need to implement a short circuit, which means that this point I need to connect to the ground. And for PCB, for example, okay, so this picture actually is a cross-section view of a PCB. This will be the microstrip line, for example, and this will be the grounding. And in order for this point to be ground, I need to drill a hole. Can you imagine? I drill a hole onto the PCB, basically that look like this, and I actually need to fill in, for example, the solder, okay, which I actually can solder the component. I actually solder to let the flux actually flow in, and basically this will be a connecting point from this point all the way to ground, and this is how we can actually implement the VR. Okay, basically the VR hole basically is to so-called denote the short circuit over here. From here, you can see that it's actually quite troublesome. And in fact, this probably will add some little cost on your PCB fabrication. And also, okay, the little VR over here, okay, we need to account for the non-uniformity, which may cause the test and measurement result to be slightly deviate away. So hence, this is one thing that we want to avoid. We do not really want to so-called apply this VR onto the microstrip line. So typically for microstrip line, we try to so-called as much as possible, we do not want to have any VR. Another possible reason based on this short circuit stub is because from this frequency response, you can see that basically they don't have a very good roll-off factor. Basically, I would say that the roll-off factor is quite gentle in nature on both the lower and the upper side. So Therefore, there is always a very attractiveness to implement an open circuit stub bandpass filter. Okay, so this diagram here on top basically show this short circuit stub bandpass filter, which I have discussed earlier on the part 18 series discussion. In this video, I'm going to discuss on open circuit stub. Basically, this diagram here show an open circuit stub. From here, you can see that basically the connecting line still remain intact, which means that we are not going to change the characteristics on the connecting line. Whatever that you calculate on the part 18 series discussion on the connecting line, that two value, for example, for this case, is still valid for this open circuit stub. However, over here, you can see that I actually add another transmission line, which is also a quarter wavelength with respect to the center frequency. So therefore, from here, I actually, instead of short circuit, I actually can implement as an open circuit. And with this, I actually don't really need to so-called drill a hole or implement a VR on this point. Hence, this will be the first attractiveness to implement a bandpass filter using open circuit stub. Next, when I actually implement using open circuit stub, you can see that the roll-off factor is definitely much better as compared to short circuit stub. You can see that because why I have a steeper roll-off factors is because I actually has a 2 transmission zero, okay, which means that this will be the minimum point of the transmission. Basically, therefore, I actually can have a sharp roll-off factor, which is quite essential for this case here. However, when we actually implement an open circuit stub, it do has their disadvantage, which I will further discuss later on. So next, I'm going to discuss what are the formulas that we need in order to design this open circuit stub in order to have a bandpass filter. Okay, remember I told you earlier on, whatever that you calculate based on part 18, okay, the connecting line value is exactly the same. And these three formula will be required to design an open circuit stub. So now instead of short circuit stub, I actually can design an open circuit stub based on these three formula. Let's take a look over here. If YIB is equals to YIA, okay, which means that this is basically Y A portion and B portion, and if these two are the same, okay, so therefore they will become a half wavelength stub. Then the stop band will have attenuation pole at the frequency f0/2. Okay, for example, if I design in the center 2 gigs, for example, for this case, okay, I will have a transmission zero at 1 gigahertz and also at 3 gigahertz. So this is what it means here. So if this YIB is equals to YIA, okay, with this constant, alpha constant, then the attenuation pole can be made to occur at frequency other than these 2 points, which means that if I control the impedance difference between Y1A and Y1B, I actually can relocate the transmission zero. So this will make this filter even more attractiveness. This type of filter will have additional passband. However, this will be the disadvantage. So what happened here is basically you can see that I will have additional passband at frequency equals to 0 and frequency 2f0 and at the other corresponding periodic frequency. So what does this mean? You can see over here, this is actually a passband. And if I use this open circuit stub, the first disadvantage is basically I will have another passband on the lower side. I also have almost quite a so-called a repeat pattern on the upper side. So this is the shortcoming when I actually implement a bandpass filter using open circuit stub. However, as I told you earlier on, I can have a steeper roll-off factor. I also can escape the VR. So hence, you can also consider to use this open circuit stub if you have another filters band stop to remove away these two. Okay, if not, you can also consider to use a short circuit stub. But this video, I mainly concentrate on the open circuit stub design. So these are the three formula. I'm going to show it to you step by step. How can we actually calculate the admittance value for this, let's say this upper section or this lower section? I'm going to show it to you step by step. How can we actually obtain all these admittance value? Let's do an example. Okay, so this example is exactly the same as part 18 series discussion. Okay, over here you can see that the fifth order fractional bandwidth is 0.5, midband is at 2 GHz, and basically they utilize this 0.1 passband ripple characteristics. So if you need to know how to design using short circuit stub, I strongly suggest you guys to look at part 18 series discussion on filter design. Okay, I will also put this video, the link under the description, so you can do this reference. Basically, you need to look at this part 18 first before you come into this part 19. So basically, this is a solution. Basically, what I want to do is basically, I want to convert this quarter wavelength into half wavelength. So this is what I have calculated based on part 18 solution. All the value, again, if you are not sure, you can always welcome to look at the part 18 series discussion. Okay, so how can we actually do? Firstly, we need to choose the first zero. Okay, for example, I want the first zero to be at 1 GHz. Remember, at the center is actually 2 GHz. I can actually strategically locate my first transmission zero at 1 GHz. So therefore, this will be at 1 GHz. And this will be pi. This is 2 F0, which is the center frequency, which is 2 GHz. Everything I actually replace them all over here. So from here, this is pi. This is basically the first transmission zero, which I want to happen it at 1 GHz. This is 2. The center frequency is 2 GHz. And from here, I can compute that this alpha is equals to 1. So this is the step number 1 to design an open circuit stub. Next, let's go to steps 2. So this is the formula, okay, to calculate, for example, the upper portion. Okay, so this is the formula to calculate the upper portion of the open circuit stub. Okay, so let's take a close look. How can we actually obtain the value for the so-called upper portion for the open circuit stub? Okay, so this is the formula which I had shown it to you earlier on. This actually classified under step number 2. Under step number 2, for example, I can actually calculate this. I will be replaced by 1, okay, which means that I'm going to calculate this value admittance. How can I actually calculate? Basically over here, this is will be Y1. Okay, Y1 is actually obtained in part 18 series discussion. Okay, so this alpha I, which I have calculated, which is 1. Okay, so therefore I do not want to include in this equation here. Tangent squared. Okay, so if you still remember, okay, we actually obtained the alpha, the beta is actually 3 pi over 8. Okay, look at the part 18 series discussion on filter design. If this is not so sure, so basically this is where I actually just substitute all the known number into this equation. Okay, so this is 1, okay, plus 1, tangent squared, and this beta is actually 3 pi over 8. So from here, I actually work out what will be my admittance value of Y1A. So this part here, basically I punch the calculator, I will get 5.828. Same as this part. So basically this is 1 plus 1, so this will become 2. And over here, this 5.828 minus 1 will be over here. So what I need to punch in my calculator, I punch all this, I actually obtain 0.4142 Y1. Okay, based on the part 18 series discussion, I can find what is the value of Y1, or if not, you can see over here, this is the value of Y1, which is 0.03525. So which is here 0.03525. I actually recalculate that the Y1A, the admittance is becoming 0.0146. So next, okay, it will be more easier, okay, because now I already know all this value here. So what I need to do is basically, I just need to do this 0.4142 multiplied by Y2. And Y2 is actually equals to 0.06937, which is illustrated here. So therefore, I can calculate the new admittance for Y2A, which is the upper portion of the open circuit stub, which is 0.02873. So next, okay, for Y3A, okay, the calculation is exactly the same as Y2A, except this will be Y3, and Y3 is actually equals to 0.06823. If not, you can see here, this is basically the result from the Part 18 series discussion. Basically, from here, I actually have another value for Y3A, or the upper section of the open circuit stub, which is 0.02826. Remember, this is actually all the admittance. Remember, the filter is actually symmetric. Okay, so therefore, I know that Y2A is equals to Y4A, which means that Y4A is equals to 0.02873. Same for this case here, Y5A is basically the same as Y1A. So hence, Y5A is equals to 0.0146. Next, I'm going to do steps number 3. Okay, so this will be the last step. I have obtained all the Y1A, Y2A, Y3A, and Y4A, and last but not least, Y5A. What I need to recalculate will be Y1B, Y2B, Y3B, Y4B, and Y5B. Okay, so let's do a quick understanding on this equation. Okay, because the alpha is equals to 1, so once this becomes 1, I can see that Y, for example, 1B will be equals to Y1A, and hence I can see that they actually has the exact numbers of admittance. So therefore, I can easily copy all this. So now instead of quarter wavelength, they become a half wavelength with an open circuit at the end of the terminal. So this is actually how I actually calculate or design the open circuit stub in order to achieve a pass band center at 2 GHz with a fractional bandwidth of 0.5. Okay, hopefully this is clear. Okay, so now I need to implement whatever solution that I've calculated earlier on the microstrip line. So now for this case here, I don't really need to drill a hole to the VR, okay, because they are actually all open circuit terminate. And let's take a look on the outcome on the frequency domain. So basically you can see that they center at 2 GHz, a pass band of 0.5 fractional bandwidth actually occur over here. I also can see that I actually have two transmissions, 0 at 1 GHz and also 3 GHz. With this, I hope you can fully understand how can we actually synthesis design a pass band using short circuit stub for a start. So if there is a need, okay, because when we actually implement this short circuit stub, the VR can be very challenging. The VR is actually used to represent the short circuit at the short circuit stub on the other end here. So hence, it is quite common for us to implement a half wavelength stub. Instead of short circuit, it will be an open circuit. However, when we actually utilize this, we have another issue. From here, you can see that basically I will have a pass band over here. I also have a pass band over here. This can unintentionally allow some of the signal actually to pass through this filter. Hence, based on your case to case, whether you want to implement a short circuit or open circuit, end of the day, you will still have a bandpass filter response. But the key difference, which I have illustrated, is basically, let's do a quick recall. For short circuit, I need to use a VR, which can complicate the whole process of design. And for short circuit stub design, I don't have a steep roll-off factor. But when I actually implement this open circuit stub, okay, firstly, I don't need any VR anymore. And secondly, I actually has a transmission zero. And if I control my transmission zero location, I actually can also make the filter a higher roll-off factor, because based on the impedance difference between Y1A and Y1B, I actually can locate the location of the transmission zero. With this, I'd like to end my discussion. Please help to like and subscribe. Once again, sincere thanks for your strong support. I see you guys soon. Bye for now.